So in today's lecture, we take up this new topic, Jobson in packed bed column. So essentially, it is a continuous Jobson column. What we had in the earlier classes, including the examples which took, those were on stage wise. So we have when a packed bed jobber, some stirred vessel in which we brought a feed in a batch system, and in contact with say charcoals or job ends, we gave them enough time, equilibrium time. Then we took out the stream, the treated stream, brought to the second stage where again we brought the fresh adsorbents, gave them some contact. So that's how we treated our effluents. Okay, so that's the stage-wise processes. And what we do today in today's lecture is a Jobson in fixed bed column. So we have a continuous packed bed column. So certain length column, horizontal, or we can have a tower packed with molecular sieves, zeolites, charcoals, alumina, silica, etc. And then whatever gas or liquid we want to treat, which is contaminated with certain solutes, is fed to the column. And then we can imagine that as the adsorption progresses, there is some wave or a front which moves from one end to the other end as certain regions of the bed starts getting saturated. So as to begin with, it's a fresh column. So when we bring in contact with the feed which has to be treated, then first the region adjacent to the inlet will get saturated, then the next region will get saturated. So essentially there is some wave which moves, propagates from one end to the other end till the entire column gets saturated. So it's a continuous packed bed column. Now you also recall that first few lectures we had set up a very extensive mathematical expressions. So first we started with a species balance. We took a difference in elements in the packed bed column. We wrote an expression for species balance, at what rate a species is brought by convection, by diffusion, by dispersion. So that's one balance in the bulk phase, liquid or gas phase. Then we had a balance in the solid phase. So we have the porous adsorbents. So we had to write down a balance within the spherical adsorbents. Then we had one more balance for rate adsorption and desorption at the pore wall. So essentially we had a very extensive mathematical set of partial differential equations or ordinary differential equations which have to be solved with certain initial conditions, boundary conditions. It's a very, very mathematical rigorous. For this course, we said that we avoid that type of problem. Of course, we talked about mathematical approximations. One can make 1D approximation, 2D approximations. Okay, we talked about LDF, linear driving force approximations. Okay, in today's lecture, we also talk about one of those approximations, except that we bring in two new parameters, which is very handy, very good engineering parameters, MTZ, so mass transfer zone, and LUP, length of unused bed. So these are the two new parameters which will be addressed in today's lecture, and we will see how we can use them to scale up in scaling up a packed bed column. Okay, so today's lecture, it's on continuous packed bed. It's an approximations of a very rigorous mathematical, otherwise you will have a very rigorous mathematical expressions, but we will address these two quantities in this class. Okay, so let's begin with this today's lecture, adsorption in fixed beds or fixed bed columns. So these are all packed bed columns. So schematically is maybe you have a tube or a column, could be vertical as well. It's packed with adsorbents. So these are, let's say, adsorbents packed in this column. It has length, say, L. We have diameter D. Particle diameter, let's say it's dp. It's a total quantity is weight kg. We can have external area, S external, meter square per gram. We can have BT area, total area for adsorptions, meter square per gram. Bed porosity epsilon B, particle density rho p. And here we bring in contact, or we challenge this packed bed, which is initially clean, fresh, no solute inside, with certain level, let's say 1 here, or C in. So certain flow rates, Q is standard liter per minute for the gas, or for the liquid we have liter per minute. We know the density rho L and rho G. So we bring in contact here, and we are interested in monitoring this concentration profile, C with time, how does it profile at the outlet, it changes. Of course, if you recall in our lectures, we call this as a breakthrough curve, and we had a very rigorous set of equations. So breakthrough curve, or we have breakthrough response here. So in this case, we will have to, if we want to address mass transfer, then we have to make species balance in the bulk fluid or in the bulk phase, whether we have this gas or liquid. All right, and then we have to make this species balance in the solid phase as well, which is adsorbent. Okay, and when we say species balance in the bulk phase, then essentially we will have to put dispersion or diffusion on what we call interphase mass transfer or interface mass transfer rate here. And when we write this species balance in the solid phase, then we are talking of pore diffusion. So there is one rate because of pore diffusion or Knudsen diffusion. So here we are calling it intraphase mass transfer. So we have interphase mass transfer, and we have the second set of equations given by this intraphase mass transfer. Okay, so say for the first case, if C is the concentration, we have del C over del T. This is a function of bulk phase concentrations. We are also talking of concentration at the pore mouth. We have dispersion in X direction, dispersion in R directions. Mass transfer coefficient becomes another parameter here. Okay, then one has to write the balance within the pore of the solid. So this is del Cp over del T. This will also be a function of, say, the gas phase or liquid phase. Then inside the pores we will have Knudsen diffusivity or pore diffusivity. Then at the wall there is a rate at which species is getting adsorbed or dissolved. So CS here is solid phase concentrations, adsorb phase. So we have third set of equations, which would be, say, function of gas phase concentration, solid phase concentrations, and maybe there is a rate of adsorption and a rate of desorption. So all these three sets of equations have to be solved very rigorously, very mathematically. It's quite complex to solve. Then we talked of approximations. So generally one makes approximations. LDF is a very common approximation, linear driving force approximations, 1D, 2D model, etc. Essentially what you use here, we assume the rate of change in the surface phase concentration is very fast. In other words, one can write as rate of change in the gas phase or pore in the pores, and then we have dCs over dCp as slope of this isotherm. So one very common example is that we assume that all rates are quite fast. Everything is controlled by at the end rate of Jobson and desorption. So there are similar and different ways of approximations. We said that we will stay for this course. We will make only very simple calculations. The one very common calculation here, simplified, is concept of this MTZ. So what we are talking today's lecture, approximations for a scale up or a scale down for packed bed columns. So here first let's introduce two terminology, MTZ, which is mass transfer zone, and here we have one more, LUB, length of unused bed. Okay, so let's address first here, before this, breakthrough. Of course, just now we talked about breakthrough is nothing but the response at the exit of the column. So suppose we have this packed bed here, which is T equal to 0, it's fresh, and we have challenged this with certain concentrations. Say, let's say make it 1.0 non-dimensionalized. Then this is a Z, and let's say that in the R direction concentration profile is negligible. Okay, so to begin with, you will expect that first certain this region will get saturated, and slowly this other regions will get saturated, and there is a wave or front which is going to move from the left to right direction. In other words, if you want to plot concentration profile, you will expect similar to this at different time here. So to begin with, it was 0, now it has moved in this directions, now it moves in this directions. So concentration profiles slowly it moves in this direction. So this would be increasing time, so that this bed is actually clean or very clean here. Then some more region gets challenged or gets saturated, so concentration level rises. Then we have this another movement here, so slowly, so this bed is now till here. If we talk about this profile, this now entire bed is now saturated here. So essentially we have this concentration profiles. So if we take some snapshot, so depending upon when we have taken the snapshot, we will expect that at any time t arbitrary we have profile something like this. Alright, this bed is now saturated, and till here all these beds are now clean. So it's a clean bed, and this is saturated bed here. Some zone is here, some region where the bed is partially saturated. Okay, we'll come back to this. So this is a concentration profiles or snapshot with the time. On the other hand, one can do some different type of experiments. If you have a packed bed column and we have challenge like this, one can take, let's say one takes a samples from different locations, right? In other words, we want to monitor how does the concentration profile change here, this locations, at this locations. Okay, so you will expect that as you go along this Z length, then this length has got saturated earlier. If you monitor the concentration here, then this has taken a slightly longer time. Here it has taken a longer time like this, and at the exit we have a profile like this. So this is what we call breakthrough response. In practically what happens, you cannot take the samples all the time from the different locations, because this will disturb or may disturb the concentration profile inside. So very often what we are interested in measuring the concentration at the exit. So this is C exit with time. Okay, so this is called breakthrough curve. So we are saying that concentration is a function of time, it's a function of Z as well, and what we have measured here or what we have plotted here is C with different time at Z equal to L. So that's your breakthrough curves. If you can plot all of this in one, so we have profiles like this, like this, like this. So this is increasing length, and this is time. So we are plotting it for different lengths at different times, and in earlier we had plotted C with along with Z for different time, where we got a profile like this. Alright, so you must understand, so this is your increasing time and this is increasing length this way. So this is your concentration history, concentration history at different location. Alright, so now let's come back to this exit concentrations. So we are monitoring the concentrations like this, C over C exit. So this is 1, this is time here. When the bed becomes saturated, then the concentration reaches same level as the inlet, 1 here. Okay, and what you will like, from the practical point of view, you will like to suppress this breakthrough. In other words, you will like to develop an adsorbent which for the same conditions which will increase this time here. So this is called suppression of breakthrough. So that's what industrially point of view, suppression of breakthrough, one has to optimize operating conditions, or one has to choose a superior performance of adsorbents, which will increase the breakthrough time from here to here. So it's a suppression of breakthrough. Okay. All right. So now we would like to further discuss on this column, horizontal column, and let's see at certain time the profile. So this is increasing z here. This is z equal to 0. This is z equal to L. We have certain regions where the profile has gone like this. All right. So all it means that the entrance here is completely saturated, and this level somewhere in between 0 and say L1 concentration is in less than say C0, but it's greater than 0. So this is a zone where the bed is active. So when we say that the bed is active, we are saying that there is adsorption and desorption. It's a reversible process. So in this region there is an adsorption and there is desorption. However, there is a region here where there is no activity. So this is the region where we say that this is unused or unspent, or it's a fresh adsorbent bed. So it's a fresh bed here. Now after some time you will expect that now this column, this zone will further move. So now some more bed region has been completely saturated. So this is the region where the bed is now completely saturated, and there is certain region here where there is an activity, bed is active. So look at this profile, which was like this at the inlet, now it has moved like this, and this is a region where the wave has not reached or the bed is still active. So now let's mark this point, let's call it L2 prime and L2 here. So this is the region where we are saying that the bed is saturated. This is the region where the bed is active, and this is the region where the bed is fresh or unused. All right. So this is what we call here is MTZ, mass transfer zone. So what is mass transfer zone? It's a zone or certain region of this packed bed column which is dynamic in nature. It's moving from here to here, this locations. It moves very thin region here, and the regions ahead of this is completely saturated, and the region after this is fresh, where the activity of adsorption desorption has not yet arrived here. So this is the region of mass transfer zone. We will see its significance in the next slide here. Now if you plot further down, so after some time you will expect that now the bed, this MTZ, has arrived almost at the exit. That means now the profile is like this, and this is the region which is now totally saturated. So this is a saturated zone, and this is a region where we say that there is an activity or it's an active zone here. All right. So now we have reached the region of L3, and let's say L3 prime. If we further wait, then of course this MTZ, which is going to go further smaller and smaller, and this concentration profile will increase, and it will increase like this till the entire bed becomes saturated. So as per our definitions, we say that MTZ is, say, starting from beginning L1 L dash prime, or L2 L2 prime, or we have L3 L3 prime. So that's the M mass transfer zone here. Okay. In reality, it turns out to be that this mass transfer zone is very small, or 4 to 5 centimeter. So what is the significance of this number? If you have a column like this at any time, no matter how long is the column or how much is the quantity of adsorbent here, there is only a small zone MTZ which is active. This zone here is totally useless here. It's spent. It's already saturated. This side here, this zone, it's not active. It's a fresh adsorbents. That means this is the only region here where you have some activity, or here you have adsorption and desorptions. All right, and this also brings this argument also brings to another very important thing, what we call is PI, or process intensifications. All right, so without getting too much in details of this process intensifications, we are trying to say it here that since we realize that at any time mass transfer zone is very small, so let's say vertical column, we have this the zone which is MTZ. This is the region which is saturated, and this is a region which is unsaturated. So to ensure that we make full use of this entire quantity at any time, one way of intensifying process is that one can bring this feed like this. All right, so this one example of process intensifications where you put some valves in each of this stream, and as the wave propagates, this feed can also be moved upward, up of this front, so that at any time whatever feed is brought, it's brought in contact with this mass transfer zone. In other words, if you have the feed here, then you will see that if this bed is saturated, then entire this feed has to elute. There is an elutions. So it's essentially this is ineffective. All right, this is a zone where nothing happens. So it's a wastage of this spent adsorbents. One has to regenerate this. So activity takes place only here, neither here nor here. So there's one way of process intensifications which is quite interesting to note that. So there is a wave which moves, which represents the front. So there is a propagation of this front in this directions, and one has to make his feed move like this to ensure that at any time this feed comes in contact with this process is intensified. Essentially, one can show that we require a very small amount of adsorbents in comparison to this conventional process here. So now let's go back to on this MTZ. We said that now we have a column, and let's say now mass transfer zone has reached this level here at the exit. So let's make a profile like this. This is MTZ, mass transfer zone. Okay, total length is L here, and let's mark this number as LB. Okay, now when the wave reaches here, or when the profile reaches towards the end, if you want to monitor the exit concentrations, you will also expect that when it reaches here, we have a certain time TB, very zero concentration or very small concentration appears here. And once this further moves, this wave further moves, you will expect that this profile will also increase till this reaches one level. So if we call this as a TE, this will correspond to this region L here. Okay, now let's expand this region here. So let's take a larger views. Okay, so if we take a larger view here, so now we are saying that we have profile like this. LB is the length where the breakthrough appears. So when any observer he monitors, when the wave profile has reached here, he will monitor a very zero or very small concentrations, and as this moves here, he will monitor this concentrations. So this is LB, this is the total length of the column. Let's put a break here. Here we have all this region which is completely saturated, and when it becomes 1, we have this TE, this time for equilibrium. This is 1. Okay, we are plotting C exit over C in here. Now let's see what this area represents here. All right, so if we choose this constant level here, this distance here, then this is the level of concentration here. If we choose here, that means this bed is partially active. It's a partially saturated. It has to reach 1. So one can say that this shaded region here represents the region which is unspent or fresh adsorbents. Okay, this is a region which we can say that this is partially saturated. Now what we do, we define one more quantity here is Ts, stoichiometric time. So what is the stoichiometric time? We are saying that let's draw another line here, vertical line here, at certain length Ls. Corresponding to this, there will be another time here, which is Ts, so that this area here is equal to this area here. So what is the meaning here? We are saying that this entire area, so suppose we mark as A, let's say this is B right here, C, D. So A, B, C, D, this is the amount which represents or equivalent to the amount which is unspent. Okay, so fresh. And now I draw this line so that this area here, A, B, say E, is equivalent to Ls, B, C, or equal to Ls, B, C. So now if I take this area and put it here, as if I have now the entire region like this, which is unspent. So all we have done, we are saying that this area is partially spent, partially saturated, because this has not reached 1 yet. This is 0 here, this is say 0.5 or 0.6 here. Now all I do, since this area is same as this area, I can say that entire E, D, C, Ls, B, this is the area which is unused, and that we will call it as LUB here. So we have defined in length here Ls, so that this area is same as this, and we call it equivalent time on this exit profile as Ts, stoichiometric time. Now here also this area is now same as this area. Alright, so if we define Te, when the concentration level has reached 1, total area will be uptake, will represent the amount of solute which has been adsorbed, and this area will represent underneath this curve as the area which is totally unused. So similarly here also, the way we say that this area can be brought here, this area can also be brought here. So this will also represent very equivalent to this LUB, length of unutilized bed. Let's redraw this aspect. So now we are talking of MTZ and LUB. So we will redraw this. We'll take a, let's make a break here. So we have LB, length corresponding to this, B for breakthrough, so that we have a profile like this. This is MTZ. This is the total length L here. This area here is same as this area. Okay, so that we can say that entire A, B, C, D, entire area is now fresh. All it means, if the wave or the front is ideal or stoichiometrically like this. Alright, so breakthrough curves, if you recall, we said that profile propagates like this. Alright, why it happens like this? Another way of explaining that, if everything is ideal or there is no dispersions, or all kinetics are fast here, all rates are fast, pore diffusion, mass transfer coefficient, interface mass transfer, and everything is decided by the rate of Jobson desorptions, one will expect the front to go like this. So what we experience in a practical sense, we have the curve like this, which is non-ideal, some kind of things. Had this been ideal, our response of this breakthrough curve would have been like this. So there is a non-ideality. What we see here is profile like this. So there is certain region which become active ahead of this Ts, and there are certain region which is also active after this TS. So this is all because of dispersion effect. Had there been no dispersion effect, we would have ideal situation like this. Front would have moved like this. But now we have profiles like this. So coming back to this, we have defined this LS, length of a stoichiometric front. We can call it an ideal front, so that this area here is like this, and we can say that the entire area here is unspent, and we call it LUB, length of unutilized bed. So MTZ, you can say that it's approximately twice of this LUB here. Equivalent to this, if we draw a response here, we have the front like this. When the bed was here, when the profile has reached in the last stage of this MTZ, there will be a TB, breakthrough time, corresponding to this LB. There will be TS, so that this area is same as this area. This is 1 here. And then finally, when the bed gets saturated, we have T equilibrium. So we are talking of this front. We have introduced one MTZ. We have introduced a second quantity, which is LUB, and we can also introduce another quantity here, US, which is the speed of wave, a Jobson wave or front. This is a Jobson wave or a Jobson front. This is also meter per second, but this US is not equal to fluid velocity, mind you. This is a Jobson bed. Ideally, the wave would have been like this, but because of dispersion effect, certain region in the bed gets active earlier, and certain region gets active later than this TS. Okay, so now with those introductions, we can make some calculations here. That L, if we look at, minus LS is nothing but LUB. Okay, so you should always keep these two figure in mind. Like this, we have L, we have LS, sorry, we have LB, we have LS, and here we have, so L minus LS. Okay, so L minus LS is your LUB. This is star, or this is star. Okay, and equivalent to this, we have a stoichiometric time, where we have this TS, where you have this TB, and now you have this T equilibrium when the bed is completely saturated. So LUB equals L minus LS. What is this length here? Had the wave, would have been ideal. Had it reached here, so we could have said, and since this area is same as this, we could have said that now the bed is completely saturated. That means this L is nothing but US, the speed of the wave, into TS, the time at which this area is same as this area. So make a note here, L is US into TS minus LS. So LS is here, that means this is US into TB. So let's try to understand this again here. The wave we have drawn like this. Ideally, the wave would have been like this. This is the wave, it moves in the bed. Stoichiometrically, this should have moved like this, would have been like this, like a snapshot. Similarly, the breakthrough profile is like this, it moves like this in the bed. Ideally, would have moved like step functions. So we define this quantity LS, and we move this region from here to here, or we move this region from here to here, to make a note that we can write that this length gets saturated when the front has reached LS. So that is US into TS. And then we have this LS, which would be US into TB, the time at which the first breakthrough takes place. So that time the front is, ideal front would have been right here. Okay, so we have US TS minus US TB, length of unutilized bed, which is this. We take common here US TS. We have 1 minus TB over TS. US TS is note down again, it's L, length, total bed length is L here. 1 minus TB over TS. Or we can write L equal to LS plus LUB. We can also write MTZ as approximately twice of LUB. Why approximately? Because generally if the waves are symmetric like this, or breakthrough curve is like symmetric like this, it will be approximately twice of length. Otherwise, for to calculate MTZ, there are several correlations one has reported here. So based on these arguments, now we can take an example. So before we take this example, let's qualitatively discuss what we have said so far. So we are talking of a non-ideal response because of dispersion effect, and we talked about this stoichiometric or ideal front, the way it moves. So we define a quantity like Ts or Ls. So when the wave reaches at Ls, as if entire bed is saturated, because we chose the area accordingly. Okay. So with these two quantities, Ls, LUB and MTZ, we will take this example. Also important to note here is that what is the uptake. Now this uptake also we have talked in our earlier class. From the breakthrough response, if you find the area above the curve, that area should be equivalent to how much is the amount of solute which has been adsorbed. Okay, so just for our own purpose, let's go through that definition for this uptake, or how do we calculate uptake from a breakthrough curve before we take up this example here. Okay, so this is the breakthrough response here. This is 1. This is area, if you say it's very small TB. Now of course breakthrough is 0, and maybe for our simplicity we can say that when this area or when this response becomes 2% of the total response, maybe you can say that now the bed has started breaking, or the concentration or the bed has started becoming saturated. One has to stop here. So it's all ill defined here whether it's a 10% or 20%. For our purpose we say that it's 2% here. Okay, then we had drawn this Ts, stoichiometric time, so that this area is same as this area, and then we had this Te. Okay, now if we want to measure how much is the total uptake of this solute, one has to make this balance across this column. So Q is, if the Q is the flow rate, C0 say it's inlet concentrations, so Q into C0 is the species mass which gets in for that solute, minus Q C exit, which is a function of time here. So this is the mass at the outlet multiplied by del T. So essentially between here we have chosen a time T, arbitrary time, and we have this dt here, or del T. So this is the concentrations C, which is a function of time. So we have in minus out. Alright, so what happens to this area? This area is amount adsorbed between T and T plus dt, in minus out. So that's the difference will give us how much amount has been adsorbed between T and T plus del T. So if we integrate this, total amount adsorbed would be Q C0 minus Q Ct dt. From 0 to this Te, this will give us total amount of solute which has been adsorbed. So this will give us how much amount of give or uptake. This is called the uptake of the solute. Very often we express in terms of gram per gram. That means total amount divided by the total amount of adsorbents. So anyway, coming back to this, Q is a constant, C0 is a constant. One can take out QC0 outside. We have 0 Te 1 minus Ct over C0 dt. So this is a total amount of this. And what is this number here? 1 minus Ct over C0. Look at this curve. This will give us, you should convince yourself this is nothing but the area above this curve. So let's, if we redraw here any breakthrough curve, if you draw like this, if you measure this area will correspond to this, starting from 0 to Te, or for that matter it's T infinity. This is all your first order. This will reach almost infinite time to reach 1 here. Approximately maybe it has reached 99% of 1 or exit concentrations. So this is the total uptake. Now if we know this total uptake, so on the same argument one can calculate how much of the amount has been absorbed at the breakthrough time. So if we denote by WB, this should be same as say Q into C0, 0 to TB instead of TE, 1 minus C over C0 into dt. So we can draw the curve here. So what is this? This represents the area till tube dB. How much amount has been absorbed so far, starting from 0. So this is your WB. How much amount is absorbed till WS, which we have defined like TS here, so that this area is same as this area, is stoichiometric or ideal front. This would be Q into C0, 0 to TS, 1 minus C over C0 dt. So that would be the area till this TS above the curve. Okay, and then so once we are convinced this is WB, WS, one should go back and calculate LUB, length of unused bed. So what was the length of unused bed? We said this is the length of unused bed, TS to this final T, or this LS to final this LUB. So LUB, going from the same definitions, it was L minus LS, total column minus LS, same cross sectional area. That means you should be able to convince yourself this is nothing but 1 minus WB over W total, which we have calculated, into this length. So we could take L outside, is nothing but L 1 minus LS over this L. LS corresponds to this TB, right? So when we have the total bed saturated, you call L, we said that US into TS, and this LS was US into TB. So you should look at both the figures, this MTZ, profiling this MTZ and this breakthrough profile, to convince yourself that LUB can also be determined from here. 1 minus total amount at job till breakthrough time, and the amount total till this TE time. Okay, now we can take this example. So let's say we have a packed column. We have certain constant, it's a fresh packed bed. Let's say the length is 15.2 centimeter. It's packed with charcoals. So let's say we have this granular activated carbon. Bed porosity is 0.36. Flow rate of this effluent, say wastewater, Q, or some gas, let's say it's 80 cubic centimeter per second. So whenever you say this gas volume, one has to specify this pressure and temperature. Let's say this is at whatever P and T we have, the flow rate of the gas is 80 cubic centimeter per second. This has the inlet concentrations, C inlet. So let's say certain volatile organic compounds, undesirable compound it contains, at 190 ppm. So what is ppm? It's all volume for the gas, it's volume by volume, right? It's 190 10 power minus 6 mole fraction. So it's 190 ppm here. Okay, diameter of this column is 2.3 centimeter. And for the system, whatever VOC we have and whatever charcoals we have, so this experiment was done at this flow rate, and then we got certain data. So this was experimental data, one obtained like this. This data reads something like this. Let's say 141 minute, 154, 166.7. These are different minutes. One has noted what was the concentrations. So this is different time, and we note here certain concentrations which has been non-dimensionalized with respect to this inlet concentrations. So 0 0, all it means till 154 minutes, or let's minutes, there was no concentration monitored at this exit. After 166.7 minute, very small concentration 0.018 is measured, and so far, and after 350 minutes, maybe it's reached 1, 338, it's reached 0.9. So look at this, it's very slow. When the bed start getting saturated, response goes very slow here. It takes a very long time to come close to this one here. Okay, and the question asked here is that calculate mass transfer zone. All right, what is this length of unutilized bed? What is the saturation capacity? of this adsorbent. So these are the three questions one can answer here. So all we do, first we plot this response which we have. So this is the time, this is C by C is 0. If you plot and draw a very nice smooth curve, it's like this. So here till t equal to 165 minutes as per the data, there is no response. 167, alright, 165 minutes there is no response, and 166.7 one gets a concentration, let's say 0.02 or whatever we have, 0.018. So this is 166.7. That means as per our definitions, we can say that very close to this breakthrough time, TB is 165 minutes. So going back to the previous data, 154 there was 0 response, then 167.7 we have 0.018. One can do this interpolations to obtain that breakthrough time is around 165 minutes. Okay, and then at 350 minutes the bed has become saturated. So the first thing is that what is this US, at what speed the wave propagates. Mind you, the length of the column was 15.2 centimeter. So what is this time, and what time we are talking of? We are talking of this TS. So ideally the wave would have moved like this. One has to do this iteration to find that how much length, at what length, or at what time actually this area is same as this area. Alright, so going back to this curve here, all we are trying to do is by iterations we are moving this line such a way that two area becomes same as this area. And if we do this, one can show that this TS turns out to be around 238 minutes. So we have TB 165 minutes and we have this TS stoichiometric time 238 minutes. So we got this US 15.2 divided by 238, which is, if you calculate, 0.064 centimeter per minute approximately. What is LUB? Length of unutilized bed, which is L total length minus LS. So we are talking of this length again here. So we have the wave like this, and we have drawn this LS. So this area was same as this area, equivalent to your breakthrough profile. So this is your LUB, length minus LS. So this is LB, this is the total length. So we have L minus LS. L is 15.2. Yeah, what is LS? US into TB. So essentially the wave front ideally would have reached here. Had this been ideal, then the bed would have saturated. Had it reached here, then the bed would have saturated till LS. So minus US into TB. Alright, and we know these two quantities, 15.2 minus 0.064 into 165. We calculated from our breakthrough profile. We made some very small approximations. Data was given for 0 till 154 minutes, and at 166.7 we had this data of 0.018. So all you can do, you can draw a smooth curve through this to find out at what time it's just about to break. Okay, so that's your 165 minutes. So we put this number will be 4.66 centimeter. Mind you, with this number will also be same as, if you calculate directly, 1 minus TB over TS. We know the breakthrough time 165 minutes, and we know the stoichiometric time TS, which we calculated from there as 238 minutes. Both will give the same results to obtain this 4.66. So what is this MTZ? MTZ is approximately twice LUB. If you plot, you will see that this is symmetric. It's a symmetric response, or the breakthrough profile is like this. It's symmetric about this TS or LS. Okay, so that's the way to calculate this MTZ, mass transfer zone. What is the physical meaning of this mass transfer zone? The idea here is that if you take a small column or if you take a larger column, as long as the operating conditions are the same, then this mass transfer zone remains the same. So one can do this experiment on a smaller scale to calculate this MTZ. One can scale up for a larger column. So this becomes a very engine parameters. For this course, we remain confined ourselves to this level of discussions. Otherwise, we can go through some different textbook or higher level textbook to get more comprehensive design of a Jobson column based on this MTZ or this length of unutilized bed column. And the last column we have, last answers question we have to answer. What is this saturation capacity? So what is the saturation capacity? That's very easy to find out. Just find out the area above this curve. Alright, so one has to integrate, or one can make some approximations finding out how much is this area and how much is this area. So saturation capacity is nothing but milligram per gram. How much milligram of adsorbent VOC has been adsorbed per amount of this adsorbent. So how much it has been adsorbed, you have to want us to integrate Q C0, 350 minutes, that's your saturation time, 1 minus Ct over C0 into dt. Essentially this area under the curve, either you solve numerically, you know all these data points, make use of certain numerical methods to calculate this area, or even approximately one can measure, assuming that's rectangular, maybe this is very close to the triangle, so half length into height here, divided by the total amount of adsorbent. So all this quantity we know, this Q is 80 cc per second. This C0 we know how much ppm we have. We can convert this ppm in the gas volume to some milligram per gram. Mind you, for the gas this is volume by volume. One can make some stoichiometry here to convert this to this milligram per gram as well. C we know the response, C0 is again known to us. We can integrate from 0 to 350 minutes. What is the total amount of adsorbent we have used? So we have the total volume pi by 4 d square, that's the diameter of the column, into the length. So this is the total volume of the column into 1 minus epsilon b. So bed porosity was given 0.36. So this is the total volume of your particles, adsorbents, multiplied by the particle density will give you this W here. So this milligram per gram would be your saturation capacity corresponding to this 190 ppm. What does it physically means? It's also very important that we understand that we have done this Jobson experiment or isotherm experiment where we have this isotherm like this. Alright, so where we plotted milligram per gram, say Langmuir isotherms or BT isotherms or Temkin, Q versus this concentration milligram per liter, Cl aqueous phase concentrations or partial pressure of the gas or concentration in the gas phase or ppm mole fraction, etc. If you take this 190 ppm and read this number, this milligram per gram must be the same as what you have calculated just now from this breakthrough analysis, the area under the area above the curve divided by the total amount of this adsorbent. The two number must be the same here. This is the exercise. You must check yourself for the system, whatever you do address, the adsorption which we have done in the batch conditions. This has to be same as what we have done in this column experiment, because it's just a question of time. Here maybe the time is different, here the time is different, but at the end of the equilibrium, when the bed is saturated, the entire adsorbent column is saturated with this 190 ppm. If you do the batch experiment, no flow experiment, even there this 190 ppm of vapor will give you the same loading here. Alright, so this is the example we have taken for this adsorptions for this column experiment. As we said again, we repeat that column experiments may be simpler to do, okay, but when you want to do this mathematically very rigorous analysis to find out the response or to predict the response of the breakthrough curves or how much is the saturation capacity, it's a very extensive computational exercise, mathematically very extensive. One has to get into the higher level or graduate level of courses on adsorptions and see what type of calculation one can do solving this partial differential equations. For this course, whatever we have done is stage wise at the third year level, that's one thing. For the column experiment, our maximum computation will be limited to the calculation of MTZ and LUB, length of unutilized bed. Okay, What is the physical significance of MTZ and LUB? You must have appreciated. You may not have appreciated what is the utility, how do we scale to a large practical columns. That again, when you get exposure to the graduate levels, you will see those difference. The more important here is that whether it's a column experiment or the batch experiment, when the bed gets saturated in the column or when the bed gets saturated in the batch experiment, the loading must be the same, corresponding to the same inlet concentrations and the final concentrations. So that's the more fundamental of this adsorptions. So this is the end of our discussion on adsorptions. We have taken several examples, couple of examples. The rest of the examples are given in the textbook by Trebon, by Dutta. Solve examples or the problems here. It's strongly recommended that you try to solve those problems on your own. Okay. Next time when we meet, we take up a new topic, new unit operations. That's a drying. Okay. So far we have done absorption, then distillation, extractions, adsorptions, and the last unit operation we will take, that's on drying of solids. Okay.